Bingo, we're back. I'm Jay Fidel with Research at Manoa here on Think Tech on a given Thursday at 4 o'clock. Rock with Dr. Pete McGinnis-Mark of SOWEST. We are so happy to have you back again,
it's
Dr.
It's a pleasure
Pete.
to be back again, Jay.
Absolutely.
Right.
So today we're going to talk about I/O. I/O?
I/O, EO, whichever way you prefer.
Okay,
yes.
it reminds me of something in computer land, which is input, output.
Ones and zeros.
Yeah.
But just to set the stage, this is a moon of Jupiter, right? And
everyone knows that, and if they didn't, they know it now.
And presumably people know that Jupiter is the next planet out beyond Mars. So we go from Earth to Mars to Jupiter. And Io is one of the more interesting moons of Jupiter.
Why?
Well, let's start off by taking a look at the first picture, and I'll just give you some general description. Here we're seeing what are called the Galilean moons of Jupiter, because Galileo first discovered them back in 1610 when he basically took advantage of the new technology of the day, the telescope. And we see in the background Jupiter with all of its swirling clouds, and of course Jupiter is about 300 times as massive as the Earth. And then there's some fascinating moons, and I'll come back one other time and tell you about Callisto, which is at the far right, and you see it's got lots of craters on it, so it's probably old. Then bottom left, we've got Ganymede. Ganymede is the biggest moon in the solar system, and it's got a thin icy crust, but it's also got lots of craters on it. Europa, the bright one there in the middle, is probably the best bet where we might expect to find life elsewhere in the solar system. Arthur C. Clarke's 2010 novel, for example. All these worlds except Europa are yours because Europa has a thin icy crust and probably an ocean that's at least 100 kilometers deep. But today we're going to focus on Io.
Are you telling me that there's make that 4 moons off Jupiter?
They are just the larger moons. So,
there are more?
So Jupiter and Saturn have like dozens of moons as well, but most of them are really small. The other main one is called Amalthea, which is actually closer to Jupiter than Io is, but we won't deal with Amalthea today.
No, I feel that we've been cheated here on Earth. We only have 1 moon.
That's right, but our moon is unusual in the solar system simply because our moon size is larger compared to its parent planet than any other moon in the solar system. And there is another story why our moon has had such importance in the evolution of the Earth, but it's primarily because of its size.
It had nothing to do with Valentine's Day and the tides and romance?
Its moon's certainly responsible for the tides. Whether or not you get starry-eyed looking at the moon is your problem, Jay.
Okay. Let's move right along then.
Moving right along. All right, so we sort of know that Io is a moon of Jupiter, but let's take a look at the second slide. And here we're doing a comparison so that I want you to recognize that Io is a world into its own right. So that this is an image. It's a composite, so they're not this close together, but we're comparing both our moon to the size of the Earth, as well as Io to the size of our moon and the Earth. And you can see that Io is about the same size as our moon, a little bit bigger, but basically it's about the same size. And probably initially when the moons and planets started to form, it was made of the same stuff. So it makes sense for planetary geologists like myself to actually take a look and compare what we see on Io to what we see on our moon, and how does that help us understand things on the Earth.
How did it get named Io?
I've no idea.
Just the way it is.
Next question.
There are some, some things that are fundamental.
Next question, please. Yes, no idea.
Okay. All right. So you said that it's special. We need to study it.
We need to study it.
Why is it different? Why is this planet different, this moon different from all the other moons?
We'll let the story unfold in a few minutes, but recognize that we really haven't had much knowledge of what the moons of either Jupiter or Saturn or further out in the solar system is like for that long. For example, we will see that the first spacecraft which went out to the outer part of the solar system didn't get there till, first one was 1977. If we go to the next slide, we'll actually see this is an image which was taken by the Voyager 1 spacecraft which flew by Jupiter in March of 1979. So, yeah, within living memory for at least you and me,
Yes,
Jay.
yes.
And what we can see in the top left is actually one of the navigation images. So as the spacecraft goes zipping past Jupiter, it's trying to figure out where it is in the solar system because it was going on towards Saturn. So it looked back towards these moons, partly to refine its own path and partly to refine the orbit of the moons. And rather than seeing just a dark disk, what the navigation team, a lady called Linda Mirabuto, was able to find was that if you look at the edge of the moon, there are these bright spots. And if you can put the image back again, what we can see is that basically we have not only a very thin crescent Io, all right, so the bright part on the left-hand side is sunlit and everything else is dark, but at 3 points, 2 at about 11 o'clock and 1 at about 3:30 on the right-hand side, you've got these big plumes or big bright spots. And that was completely unexpected by the navigation and science teams. And so in the bottom right, what we're seeing is a color version of other images which were taken the same day. And you can actually see that there's this big, big plume coming off of the surface. And the height of that bright point there, sort of top left, that's about 500 kilometers, or about 400 miles. So these are very bright plumes, and it was one of the puzzles before we got this image. Notice a lovely pizza-colored moon, for example. Geologists, as the spacecraft approached, were trying to figure out, well, how does this have such a bizarre color? There are no meteorite craters on the surface, so we know it's a very young surface. Well, it turns out that Io has more active volcanoes per square mile than Earth does or anywhere else in the solar system. So what we were seeing in that image is a plume rising off of the surface, and
it's a
big volcanic eruption. And coincidentally, that big eruption was subsequently named Pele after the Hawaiian volcano goddess. So we've got Pele on Io as well. But understanding the way that volcanoes work on Io, it's really important because there's no atmosphere, it's lower gravity, and also because it's such an active volcanic world, trying to figure out, well, where's all the heat coming from? Because a small little moon, the same size as our moon, should be extinct by now. It should have cooled down early in solar system history. So volcanism is an efficient way for a planet or moon to lose its heat. There must be a lot of heat stuck in the middle.
How could that be?
You just wait, I'll tell you.
Okay.
But, all right?
Okay.
But that was one of the real puzzles early on in the mission, trying to understand not only what is it that we're looking at, what's the chemistry, how old, why do you have so many eruptions, what type of magma do you have, how does it compare to eruptions here in Hawaii, for example?
Sure.
A whole series of interesting questions.
Yes.
So as we roll on, let's go on to the next slide.
He's holding back the answers.
And
he wants to make this a cliffhanger show.
Trying to make it logical. I'm confusing you, I know. But these eruptions, they are so big that, for example, from Mount Mauna Kea telescope here in Hawaii, using the Keck 2 telescope, you can even detect volcanic eruptions on Io, like 4 times as far away on Jupiter's moon than we are from the sun. What you can see here are Keck telescope images at different wavelengths of light. So where you see down in the bottom 1.59 microns, 2.27 microns, and so on. We're looking into the infrared. And the guys who take all these data sets have shown that you've got some really high temperatures on the right-hand side. You can see that you've got just 3 really hot centers. But if you come to the left-hand side, you're seeing that basically the whole moon is unusually hot. There's some very strange characteristics. So one of the things that researchers try to do is to figure out how much heat is produced by Io compared to, say, the power generated in the United States or volcanoes here on the Earth each day. What is powering them and that sort of thing. So
how do you do that?
Well, I mean, there's a variety of techniques. Spacecraft which are coming close to Jupiter can get much more precise measurements, not only of the size of these eruptions as well as their temperature. So they use a spectrometer basically to measure the temperature, but also they can look at the orbit of the moon and try and do some physical modeling of what the orbit is like in comparison to the other moons and that sort of thing.
What does that tell you?
Well, I will show you later on that it tells you that Io has a very unusual orbit insofar as it goes around Jupiter twice for every time that the next moon out goes around Jupiter, or I think is 4 times for the moon beyond that. And we'll see a little in animation or a graphic later on, and I'll explain more about that.
So that 4 times
is very
connection
significant.
is significant because that will help you understand about the weights.
Not the weights, it will tell us what the tides are. Just as Earth's oceans have tides, and they get sloshed around the Pacific Basin, that sort of thing. Think of Io having tides not in a liquid, but in a solid, or a molten rock.
A magma kind of tide.
We'll see in a few minutes.
Slosh tide.
Let's move on there. One more slide before the break. And this is just to illustrate the size of some of these eruptions. On the left-hand side, bottom left, that is the surface. You can see there's a little mountain in the middle, but off to the top right, all that white filamentary stuff, that's an explosive, that's like a Mount Pinatubo ash deposit, but it's 600 kilometers high, or over 500
Is it
miles.
active, or is that the residue of it?
It's active. It's been active continuously since the first spacecraft saw it in March of '79. So whatever's powering this particular eruption is way more energetic than what we have seen here on Earth with Mount Pinatubo or Mount St. Helens, or any of the other much more violent explosions in the past.
We have to find out why.
We have to find out why, yes.
Yes. When are we going to find out why?
Probably in about 5 minutes' time.
Okay.
I'm Ethan Allen, host of Likeable Science here on ThinkTech Hawaii. Every Friday afternoon at 2 p.m., you'll have a chance to come and listen and learn from scientists around the world. Scientists who talk about their work in meaningful, easy to understand ways. And you'll come to appreciate science as a wonderful way of thinking, way of knowing about the world. You'll learn interesting facts, interesting ideas. You'll be stimulated to think more. Please come join us every Friday afternoon at 2 p.m. here on ThinkTech Hawaii for Likeable Science with me, your host, Ethan Allen.
Hello, my name is Crystal. Let me tell you, my talk show, I'm all about health. It's healthy to talk about sex. It's healthy to talk about things that people don't talk about. It's healthy to discuss things that you think are unhealthy because you need to talk about it. So I welcome you to watch Quack Talk and engage in some provocative discussions on things that do relate to healthy issues and have a well-balanced attitude in life. Join me.
Bingo, we're back. Research in Manoa with Pete McGinnis-Mark and Io, or EO, as the case may be.
That is correct, yes. So let's continue just this slideshow of some of the landforms, because it's a really fascinating world. So if we go to the next slide. For example, they've got funny names. With Tupan Caldera, you know that Kilauea has a caldera at the summit, and so does Mauna Loa. Here we're seeing on the left-hand side a color image, and on the right-hand side is a temperature image, and it's not calibrated, so I'm not telling you degrees centigrade or Fahrenheit what the surface is like, but it's of exactly the same area. So we can tell that this landform is like an active overturning lava lake, just as the lava lake in Halemaumau crater today, for example, is continuously active. Here we're seeing hot lava in what appears to be a solid surface, and it's the dark stuff which is really hot. The next slide will show us that not only do we have to worry about lava flows with the same chemistry as the ones which we have here on the Earth, But it seems quite likely that there's a lot of sulfur near the surface of Io. So the little sort of, on the left-hand image, where we're seeing that bright yellow spidery sort of thing with the blue arrows coming from, that we think is a sulfur lava flow. So it expands our range of ideas or possibilities for what would a volcano somewhere in the solar system
But we
be like.
start thinking perhaps yellow planet, funny color, sulfur, yellow, maybe there's a connection?
Of course, yes. So that a lot of the surface is an allotrope of sulfur, so it's a particular way that the atoms are bonded together. And indeed, the yellow part of Io is indeed covered with a sulfur frost. And depending on how high the eruption plumes go, you may quench that sulfur, so you have a second different allotrope. So it's frost, and the really hot sulfur is black. Sulfur is a really interesting.
This is like a mystery
It's great.
unraveling.
And I should have pointed out, down in the bottom right-hand corner on this image, you've got, again, the same temperature image. This was taken in February of 2000. And you can see that all of those dark spots on the disk of Io in the top right, the black things, they're all active volcanoes. They're all active volcanoes. So let's move on to the next one. And this is meant to be an animation, and of course, I wasn't able to provide an animated GIF, but basically, it points out to us that Io is in what's called a resonance with some of the other moons. All right, so that in this diagram, we've got Jupiter in the middle, then the next ring out is Io, 1 to 1, so it goes around Jupiter once, but it goes around twice as fast as the next moon out called Europa. And it also goes out around 4 times compared to once for Ganymede. Here is where we get to the point of trying to understand the internal heating. Okay, now I've got a demonstration for you. So if we,
You're saying the speed and the heat are related?
yes,
Ooh.
here we have a visual clue. Now, hold that.
Yes.
And squeeze it really hard, many times. If you were to do it as fast and fast and fast as possible,
Yes.
what you would then find is that it starts heating up. All right, it's going to be slightly warmer. This is identical to what Io would be like. It's being squeezed by first Jupiter on this side, and then the moon's on the other, every time it goes around in its orbit. So Io is continually getting energy from Jupiter and the other moons.
Electromagnetic forces?
Tidal energy.
Gravity. What is it?
Gravity. Gravity is pulling it one way and then the other, and then the other, back and forth, back and forth, back and forth. And that is deforming it. So it's just like a rubber ball. If you're squeezing it over 4.5 billion years, it dumps a whole lot of tidal energy into the interior of the world.
Hence, it's hot.
Hence, it's much, much hotter than it would be. If Io was the only moon of Jupiter, it would be a cold, dead world. But because it's in this resonance, it goes around Jupiter
Multiple moons.
multiple times, and it's really big moons. Europa, Ganymede, and Callisto are really big moons. Ganymede, as I said earlier, is the largest moon in the solar system. So they're tugging away, and then Jupiter's tugging it the other way. And so we see this actually with some of the other moons in the solar system, but not quite as obviously as Io is experiencing.
So we can learn a lot
And
from
the
that.
volcanoes are how the moon is losing its heat. All right, so all the internal tidal energy inside Io comes to the surface and either produces lava flows or it produces the explosive eruptions.
The process continues, and it's still hot.
Indeed.
It will be hot.
And it will continue to heat up as long as it's in this resonant orbit around Jupiter with Europa, Ganymede, and Callisto further out.
Well, that's really interesting that if there was only one moon, you wouldn't have this
It would
process.
be a dead world. It would
If you
be-
had multiple moons with the gravitational force they're exerting on each other,
Look at our moon, as I'm sure you do.
it's a dead moon.
It's a dead moon. It's the same size as Io, but virtually all of the volcanic activity on our moon stopped about 3 billion years ago. So there's nothing, no recent activity. It's the only moon in orbit around the Earth. If there was another giant moon further away from Earth, then we would have a volcanically active moon.
So I'm getting the idea this is somewhat of a revelation, that you have discovered some kind of physical process here that is useful in other contexts.
I haven't personally discovered it. This is a community effort.
You speak for the community today.
Speak for the community, and it's just fabulous. There were actually some guys, Peel, Casson, and Reynolds, did a mathematical analysis which was published in the journal Science like 5 days before Voyager got there. And they predicted, hey, you know, we could have so much tidal energy in the Io, we might see evidence of surface volcanism. And yeah, the whole community was just aghast because it was a brilliant prediction of what we saw.
So what does it teach us, Pete?
What does it teach us? Well, it teaches us a lot about the diversity of volcanic activity throughout the solar system. If we are trying to do better understand volcanoes here on the Earth and the natural hazards that they represent, it would tell us something about the dynamics, the role of the atmosphere or the role of gravity, what kinds of volatiles or gases might be contained within magmas, and what kind of landscapes are they producing, that sort of thing.
Unlocking
secrets in the solar system. Let's move on. I think we've got 2 more slides. There are some nuances on Io. This is the south pole of Io, and I put an arrow pointing to where the sun's shining because it's hard to recognize that, the light is coming from the left-hand side, so the big striped thing on the left, that's a mountain, and then you've got some thin layers and that sort of thing. These mountains are 18 kilometers, or let's say about 15 miles high, way better, twice as high of Mauna Kea above the ocean floor. So this is another thing we have to worry about. And in the final slide, what we'll see also is that Io not only sort of covers itself with sulfur, but also all of the ejecta, the material which is thrown off in these plumes, goes into orbit around Jupiter, and it forms something called the Io torus, which is sort of that orangey thing. That's the orbit of Io, and it basically describes where all of this volcanic ejecta ends up around Jupiter. And so there are people who compare Io to Hawaiian lava lakes. They look at how sulfur lava flows might differ from lava flows which Mauna Loa might erupt. They look at the Pele volcano on Io to try and better understand where would you expect material from a Pinatubo-style eruption, for example, to be landing if it wasn't for Earth's atmosphere. Can we do a good numerical model of that kind of eruption? Because ultimately, what we try to do is to relate these planetary landforms back to Earth to make them more relevant. And volcanism, as we've seen in Hawaii, volcanism is really important. It's supremely important, say, like around in Indonesia or Japan or Alaska, where there are lots of natural hazards associated with not only the volcano itself, but how it interacts with the environment, producing mud flows, for example, or carrying people with ash.
Well, is there a chance that this material, whatever it is, whether it's sulfur or something else, would come up and be, you know, spread around the whole planet, kill the planet effectively?
Is there a risk on Earth?
Yes.
No, because you can't have such a violent explosive eruption. Magmas on Earth aren't generally sulfur-rich, although Hawaii has quite a bit of sulfur in. But for example, the material that's put in the upper atmosphere, like after Mount Pinatubo in 91 or El Chichon in 82, that material stays in the atmosphere for 2-4 years, something like that. And there has been a recognized drop in global temperatures of about 1/2 to 3/4 of a degree centigrade for that short time period. A bigger eruption back in 1815, Toba volcano, produced what was called the Year Without a Summer in 1816, where it snowed in June in New England. There was all the crops failed in Europe, for example. Mary Shelley wrote Frankenstein because it was such a miserable summer she stayed indoors all the time.
See how it affects our art as well.
It affects our psyche as well as the climate, and has serious implications, because not only would it affect agriculture, but present day, if you had a big eruption like that, it would certainly influence international air travel. There was an Icelandic eruption in 2010, which shut down all the airways.
Can't fly in that.
80 days. You can't fly.
Yeah. So, I mean, are you suggesting this is a possibility? I mean, that we would have an eruption of this magnitude, or shall I say magnitude?
I think magnitude would be better. Earth's history has been characterized by big volcanic eruptions. And most of those volcanoes have what's called a standard or approximate repose period, the time between one eruption to another. And we can look at the recent geologic record and say, yeah, for sure, this volcano's been active, let's say once every 50 years, once every 500 years, or whatever. So we know we've got some ticking clocks. It would be reasonable to speculate that some of these clocks, the alarm's just about ready to go on a time scale of a decade to a century. So we can't say, tomorrow we're going to have this eruption. But it would be reasonable to say, just to say you're predicting earthquakes, for example, or giant landslides, we can give you a probability of an event in the next decade or in the next 50 years, and it might be a 5% probability, it could be a 50% probability. May not, it doesn't guarantee it will happen, but also it's not very safe to assume it will not erupt in that time.
We don't know exactly, but we can make some better guesses now than we could in the past, especially after, studying Io, I guess.
Amongst other places in the solar system, Io is great.
So I see the world now, after you have described this, Pete, as a world full of alarm clocks, and some of them are going to go off. And you know what? ThinkTech has its own ticking clock.
And we're about done.
We're about done.